Module 6, DNP3 System Architectures and Communication Modes. Nudge 6.1, Architectural Flexibility as a Core Design Goal. DNP3 was designed to function across multiple physical and logical system architectures without altering its core protocol semantics. Utility communication environments vary widely in topology, scale, and media reliability, and DNP3 accommodates this variability through a flexible architectural model. The protocol makes no assumptions about network shape, device hierarchy, or transport medium. Instead, it defines consistent behaviors that apply regardless of how systems are interconnected. NAR 6.2 One-to-One, Point-to-Point Architecture. Structural characteristics. In a one-to-one architecture, a single master communicates with a single outstation. Communication occurs over a dedicated link. No addressing contention exists. This is the simplest DNP3 deployment model. Communication behavior. All requests originate from the master. Responses are always returned by the addressed outstation. Timing is deterministic and predictable. Typical use cases: small substations, isolated pumping stations, simple telemetry links. This architecture provides maximum simplicity and reliability at the expense of scalability. 6.3 Multi-drop, multi-point architecture. Structural characteristics. In a multi-drop architecture, one master communicates with multiple outstations. Devices share a common communication medium. Each outstation has a unique DNP3 address. Only one device transmits at a time under master control. Address-based arbitration. All outstations receive every frame. Only the addressed outstation processes and responds. Other devices remain silent. This prevents collisions and ensures orderly communication. Polling strategy. The master typically uses a round-robin polling mechanism. 1. Issue request to outstation A. 2. Receive response. 3. Issue request to outstation B. 4. Continue through all configured devices. Polling order, frequency, and priority are fully configurable. Hack typical media, multi-drop serial lines, radio networks, fiber loops. This architecture is widely used in distribution automation systems. 6.4 Hierarchical architecture, submaster model, structural characteristics. In hierarchical architectures, a device operates simultaneously as an outstation to an upstream master, a master to downstream outstations. This intermediate device is commonly referred to as a submaster. Functional role of the submaster. A submaster may aggregate data from downstream devices, perform local control or automation logic, store and forward data upstream, translate or normalize data. From the upstream master's perspective, the submaster behaves like a standard outstation. Advantages: reduces upstream communication bandwidth, enables localized decision-making, improves scalability in large systems. Hierarchical designs are common in large substations and regional automation schemes. 6.5 Data concentrator architectures. Concentration function. A data concentrator collects data from multiple field devices and exposes it as a unified dataset to a master. Key characteristics: aggregation of many outstations, local buffering and event handling, single upstream communication endpoint. Protocol homogeneity and conversion. Data concentrators may communicate DNP3 downstream and upstream, translate between DNP3 and non-DNP3 protocols, normalize proprietary data into DNP3 objects. In all cases, the upstream master interacts using standard DNP3 semantics. 6.6 Peer-to-peer communication. Role flexibility. DNP3 allows devices to dynamically assume master or outstation roles depending on context. In peer-to-peer configurations, a device may request data from another device. The same device may respond to requests from a third device. Role assignment is logical, not fixed. Use cases: distributed automation schemes, local protection coordination, redundant control paths. Peer-to-peer communication is carefully engineered to preserve determinism and avoid uncontrolled message exchanges. 6.7 Communication modes. Polling versus unsolicited reporting. # polling mode. In polling mode, the master explicitly requests data. Outstations respond only when asked. Communication timing is fully master controlled. Polling provides maximum predictability and is suitable for shared media environments. Unsolicited reporting mode. In unsolicited mode, outstations transmit responses without prior requests, typically used for event data, requires prior enabling and authorization. Unsolicited messages are still structured as valid DNP3 responses and are subject to confirmation and retry mechanisms. NABR 6.8 Control of Unsolicited Communication. To prevent uncontrolled transmissions, unsolicited reporting is governed by explicit enable-disable commands from the master, class-based event filtering, application layer confirmation requirements. If unsolicited messages are not acknowledged, outstations revert to a safe state and resume buffered reporting. 6.9 Media independence across architectures. DNP3 architectures are independent of physical media. The same architectural models apply across serial point-to-point links, multi-drop radio systems, fiber optic networks, TCP IP-based LANs and WANs. The link and application layers preserve identical behavior regardless of transport. 6.10 Scalability and determinism. DNP3 system architectures are designed to scale from single device links to thousands of field devices while preserving deterministic control behavior, predictable data acquisition timing, bounded network utilization. This scalability is achieved through explicit addressing, controlled communication initiation, and strict role definitions. 6.11 Architectural outcomes. The architectural flexibility of DNP3 enables utilities to incrementally expand automation systems, integrate devices from multiple vendors, support hierarchical and distributed control strategies, maintain consistent protocol behavior across generations. By separating protocol behavior from network topology, DNP3 provides a stable and extensible foundation for utility communication systems operating at scale. Module 7, DNP3 Reliability, Error Handling, and Data Integrity Mechanisms. 7.1 Reliability as a first-class design requirement. DNP3 was engineered for hostile communication environments where data corruption, signal loss, latency, and intermittent connectivity are normal operating conditions. Unlike enterprise IT networks, utility field networks cannot assume clean channels or continuous availability. Reliability in DNP3 is not delegated to lower layers alone. Instead, it is enforced through multiple coordinated mechanisms across layers, ensuring end-to-end data integrity and deterministic behavior. 7.2 Error Detection at the Link Layer, Cyclic Redundancy Check, CRC Strategy. The DNP3 link layer employs a high-granularity CRC mechanism designed specifically for noisy links. Key characteristics: CRC applied to the link header, CRC applied to every 16 octets of data payload, independent CRC blocks within a single frame. This design ensures that localized bit errors can be detected without discarding entire frames unnecessarily. Impact on data integrity. Any CRC mismatch causes immediate frame rejection. Corrupted frames are never passed upward. Partial frame corruption does not propagate into application logic. This significantly reduces the probability of undetected data corruption. NAR 7.3 Frame Sequencing and Duplicate Detection. Link Layer Sequence Control. Each link layer frame includes sequence control information that allows the receiver to detect duplicate frames, detect out-of-order delivery, reject retransmissions already processed. This is essential when retries occur due to timeouts or communication disturbances. Duplicate frame scenarios. Duplicate frames may occur due to lost acknowledgements, retransmission after timeout, temporary link degradation. DNP3 ensures duplicates are identified and discarded, preventing double execution of commands or duplicate data insertion. 7.4 Link Layer Confirmation Mechanism. Optional acknowledgements. The link layer supports optional confirmation of frame reception. Behavior. Sender may request confirmation, receiver returns an acknowledgement frame. Lack of confirmation triggers retransmission. Trade-offs. Advantages: increased delivery assurance on unreliable links. Disadvantages: increased latency, additional bandwidth consumption, potential cascading retries under severe noise. As a result, link layer confirmation is selectively enabled based on network conditions. 7.5 Transport and Application Level Reliability. Fragment reassembly integrity. Large application messages are fragmented and transmitted across multiple frames. The embedded transport function ensures detection of missing segments, detection of duplicate segments, correct reassembly order. If any fragment is missing or invalid, the entire application fragment is rejected. No partial data is delivered to the user layer. Fragment boundary enforcement. Transport headers explicitly mark first fragment, final fragment. This prevents accidental concatenation of unrelated messages and preserves message boundaries. 7.6 Application Layer Confirmation. Purpose: application layer confirmations validate successful semantic processing, not just frame delivery. They confirm that a request was correctly interpreted, the requested function was executed or queued, the response is authoritative. Use cases. Application confirmations are especially critical for control operations, unsolicited responses, time synchronization, configuration commands. Failure to receive confirmation triggers controlled retry behavior. Number 7.7 Exception Handling and Error Responses. Explicit error reporting. DNP3 defines formal exception responses that indicate unsupported function codes, invalid object groups or variations, out-of-range point indices, authorization failures, resource exhaustion. Errors are reported explicitly, not inferred from silence or malformed responses. Deterministic error semantics. Each error condition has a defined response type, a defined recovery expectation. This eliminates ambiguity and prevents undefined system states. 7.8 Handle communication interruptions. Outstation buffering. Outstations maintain internal buffers for event data, unreported changes. If communication is lost, events continue to be buffered. No data is discarded unless buffers overflow. Upon reconnection, buffered events are transmitted in order. Master recovery behavior. Masters typically perform integrity polls after outages, event buffer reconciliation, time resynchronization. This ensures master databases return to a consistent state. Number 7.9 Data quality and validity flags. Embedded quality indicators. Many DNP3 data objects include flag fields that indicate online-offline status, communication loss, data restart conditions, forced or substituted values, overrange or invalid measurements. These flags travel with the data, ensuring integrity context is preserved end-to-end. Separation of value and validity. DNP3 explicitly separates numeric value, quality, and trustworthiness. This prevents downstream systems from blindly trusting stale or invalid data. 7.10 Prevention of unsafe control execution. Multi-layer safeguards. Control reliability is enforced through sequence control, select before operate, timeout enforcement, duplicate command detection, explicit success failure responses. No control action is executed implicitly or silently. Rejection conditions. Controls are rejected if selection has expired, parameters are invalid, device state does not permit execution, duplicate or stale commands are detected. Rejected controls do not alter physical state. And 7.11 Determinism. Under failure conditions. Even during failures, DNP3 maintains deterministic behavior. Frames are either accepted or rejected, never partially processed. Commands are either executed once or not at all. Data is either validated or explicitly flagged. There is no undefined intermediate state exposed to the user layer. 7.12 End-to-end integrity model. DNP3 reliability is achieved through layered redundancy, not reliance on a single mechanism. CRC-based error detection, sequence control and duplicate rejection, fragment reassembly validation, explicit confirmations, buffered recovery mechanisms, embedded data quality flags. Together, these mechanisms ensure that data and control actions delivered through DNP3 remain accurate, auditable, and trustworthy, even in the presence of severe communication impairments. This reliability and integrity framework is foundational to DNP3's suitability for mission-critical utility automation systems operating in real-world field conditions.